Hello again. This lesson is about electromagnetism and Lenz's law. Last video, we focused on Faraday's law, which helped us determine the magnitude of an induced EMF and therefore current that is produced in the wire. And we didn't really talk about why it has a certain direction. And so that's what this video is going to focus on. First, let's do a warm-up. This is the same diagram that we saw in the last video. So which direction do the positive charges moving while the wire moves down through the magnetic field or inside the magnetic field as shown below? So we definitely have negative charges kind of just, evenly separated in this. Positive charges. Which direction do they move? So think about it. Think about corner right-hand rule and give an answer. So you can see the positive charges piling up on the right and negative charges on the left, inducing a current that's happening to the right. This is, of course, shown by this corner right-hand rule, where you use your middle finger, your index finger, and your thumb to decide the direction of F, the force on the positive charges. But why does it go right? Like, why doesn't it go left? So what would happen if it went left? So let's imagine it was going left now. So there's now current on this wire going to left. And we know that when there's a current traveling through a wire, it induces a magnetic field, creates a magnetic field around the wire. And we would use our curl right-hand rule that shows us the direction of the magnetic field as curled around the wire. So the thumb, with your right hand, you'd point your thumb to the left, and you notice that it would go into the page on the top and out of the page on the bottom. So into the page on the top and out of the page on the bottom. And what we know back in electromagnetism from SL days is that anti-parallel or opposing magnetic fields produce a force, an attractive force, whereas parallel magnetic fields or like magnetic fields produce an opposing force. So this should produce a force downward if this is the way the direction of the current was. But it's already falling downwards, or it's already moving downwards. And we know that the force that is induced is created by the magnetic field, but also by the velocity or the speed. So if a force is pushing it downward, that means the velocity is going to increase, and then therefore the force is going to increase, and the velocity is going to increase, and the force is going to increase, and the current all this time is obviously increasing as well because the velocity is increasing, right, as well. So this creates this infinite energy cycle, which can't happen. That's impossible. So this actually breaks the conservation of energy. Like where does the energy come from to induce the current in the first place, right? Like electric energy or electric power is the product of the current times the voltage. Well, it's inducing an EMF, inducing a current, and therefore there's some power, there's some energy being transferred to this electrical. So where is it really coming from? Well, then that might mean that, hey, there's not a downward force, there must be an upward force, and that must be taken from its kinetic energy or from the potential energy, right? There must be some work done that gets taken from that. So this is actually how it happens. And then if it happens like this, let's create the magnetic fields. So we should see, your right hand, with your right hand, your thumb's going to the right. So you're curling your magnetic field around the wire, and we should see it coming out of page on the top and into the page on the bottom, creating an upward force. So it's actually slowing down the object that's traveling. And now let's imagine it's actually falling. It's in free fall or something. And so we have this gravitational potential energy, and then it normally would travel and transfer to kinetic energy. But this opposing force is now absorbing or taking some of that energy. So the gravitational potential energy is now not going to kinetic energy, it's going to electrical energy. That force is there to allow for the induced current and the induced electrical energy to occur, the induced electrical power to occur. And this is Lenz's law. This is giving us the reasoning for the direction of the current. So what's kind of odd is that the current has to flow, has to be induced in such a way that it opposes the motion or the change that produces it. That's the definition. We have Lenz's law. The direction of the induced current is such that it will oppose the change that produced it. So in this case, the change is an object moving downward through the magnetic field, and therefore Lenz's law is going to induce the current, or rather Faraday's law is going to induce the current, but the direction of the current is in a way such that it will oppose the motion or the change that produced it. So that's our definition of Lenz's law. And that's a very conceptual definition. The mathematical definition is kind of weird, but really we start off with this EMF of Faraday's law, where the EMF is equal to the number of coils times the change in magnetic flux divided by the change of time. Well, where does Lenz's law come in? Like, where do we see that? And we see that in front of this. There's a negative here. So that negative is telling us that it has to oppose that change. So it's not going to produce an EMF that is in the same direction of the change in flux. So there must be an opposing flux that is created from the induced EMF. So let's see that by example. We see that here. I want to show this demonstration. Then I want you to think through this happening. So the audio is not going to work, so I'll talk through it. So here's a scientist looking dapper, and he's got this this pipe. It's a copper pipe, and he's got this metal piece, and he drops through it, and it drops normally, right? There's no difference in what you'd expect. It falls in free fall, hits the ground, all good. And then he takes this other metal piece. He's going to put this away. Right? Takes this other metal piece that's different, and it's actually magnetic. And when he drops it, you'll see that it slows down as it falls down. Quite a lot, too. So this is a copper pipe, so it's very conductive. And you might think that it's actually like scraping against the sides. It's not. When we get back to class, we can actually observe it happening. It looks pretty cool, and there are other videos that I can share that show it just kind of floating downward. So what it's doing is it's inducing a current in the copper wire or copper tubing, and that induced current is producing a magnetic field that's opposing the motion, and then it's going to slow the object down, and it actually hits some sort of terminal velocity. So it must reach some velocity in which the electromagnetic current that's induced is enough to stop it from falling faster. All right, so let's find out how to see this in terms of coils, because we just saw it in terms of wire. Wire is a little bit easier. But a coil, we need to think of this as, are magnetic field lines entering? Are they exiting? Are they North Pole field lines? Are they South Pole field lines? And so we have two variables that we're working with, and really we just look at them as, are they positives or are they negatives? So in this case, there's no relative motion between the magnet and the coil, so there's no current being induced here. As long as there's no motion between this, no relative motion, then there is no current. Also, I want to identify kind of this the portrait mode of this, like what's the left side of the coil and the right side of the coil. This is the left side of the coil, this is the right side of the coil, and I'll be often drawing like wires or the magnetic field lines passing through the coil from the inside of the coil, because we focus on the inside of the coil. We forget or we don't pay attention to the outside of the coil. It doesn't affect our data. All right, so in the situations below, first we're going to draw the magnetic fields of the induced current in these situations. So we have a North Pole that is going to be entering this coil, and it enters it in this way, right? And we'll just imagine that this one's going this way. Imagine this one actually enters this way. And so there are two variables we're looking at. We're looking at, is it the North Pole? And then is it entering or exiting? I like to think of the North Pole as kind of positive, or if there's field lines entering the coil, such as this, like the North Pole, then that's a positive magnetic field. And because it's actually moving towards the coil, Then you have positive field lines entering, so that's like a positive and a positive. So we have to decide which direction of field lines are they that oppose that double positive. Well, double positive is adding, right? So we need to subtract some field lines. The way to do that is create opposing field lines. So we need to create rightward facing field lines. And when I say rightward or leftward, I'm talking about from inside the coil. So I'm going to draw field lines that come from inside the coil and go around. I'm going to do that here as well. Right? There's an arrow, and then it's going to come back around, and then that. So we have field lines that from the inside of the coil are facing towards the North Pole. Yeah. And then this magnetic field is going to be due to an induced current. So then we have to kind of work backwards and use, okay, we're going to use magnetic field lines first, and then we're going to identify the direction of the current. So let's do that last, though. The next one is North Pole is exiting. And now, it kind of hint, right? If we know what North Pole is doing when it's entering, it's probably going to be the opposite when it's exiting. But let's think through it before we make that assumption. So let's draw our field lines. You don't have to do this every time. I'm just doing it now to kind of help us. And so we have positive field lines. I'm thinking positive leftward or north, but they are leaving the coil. So the leaving the coil, this is almost like a negative. So we can see like over here, north is like a plus, and this is like a plus. So then we have to add negative field lines or rightward facing or opposing. In this case, we have a positive, but since it's going backwards, this is like a negative. Let's make that like positive. So we are adding a negative, so we need to, in order to get back to, due to Lenz's law, we need to oppose that change. So we need to add some field lines to it. So if we're adding field lines, well, that's like adding North Pole field lines. So we're going to actually draw field lines that go like this, that go in. So since positive field lines or north field lines are being removed, we will add those North Pole lines back in. We'll add those positive field lines back in. Now, I want you to try these next ones. The ones that are, the things that is different about these is now it's the South Pole. So the South Pole is now entering, or the South Pole is now exiting. Go ahead and pause the video and try to work through this. If you had trouble with it, the hint is you can think of South Pole lines as negative, and since it's entering, you're like adding a negative. So what do you need to do to get it back to oppose that addition of the negative? So if you've already got an idea, if we're adding the negative, that means we need to get it back. We need to oppose that change, so we need to add some field lines. So we need to add, and when I say add field lines, we need to add North Pole field lines, or specifically field lines that are opposing this South Pole. So we should have field lines that are traveling in or to the left from inside the coil on all of these. Right? You have negative field lines or South Pole field lines being added to it, so we need to add opposing field lines such as like North Pole field lines. And this last one, go ahead and think through it. So we are subtracting negative field lines. So that's like adding field lines. So we need to be removing field lines or adding south, like south field lines. So we need to add field lines that are exiting this way from inside the coil, because they are being removed. If negative field lines are being removed, we need to add them to oppose the change that's occurring. So the next thing you want to do is I want you to draw the direction of the current due to the magnetic field. So this is where we're kind of doing reverse electromagnetism, in which we draw the magnetic field lines and then we identify the current that is producing those magnetic field lines. So you're going to have to use your curl rule, and I think this will work. So my hand, if I want to create a curl that's going to the right inside the coil, then my thumb needs to be facing down on this first one, which I'll call A because I think we're going to use that later. So this is going to have a downward current right here, upward current here. On this next situation, well, it's the opposite happening, so it should have the opposite. Let's find out. Yeah, because my curl should be like this. It's going to the left from inside the coil, right? So this will be going upward, going downward. Now we're taking out positives, so we're subtracting a positive here, which is the same as adding negatives, right? If we think of that, so we should imagine that we should have the same current traveling here, and we see the same magnetic fields on this top right situation to this bottom left. Whoa, bottom left situation. So we have an upward current, downward current, and then similarly, since this is the opposite way, right? You have this curl going like that. You should have a downward current here and an upward current here. Now, one thing that to remember is that these are the four situations you'll see with coils and magnets. But there's one thing different about a coil versus a straight wire. A straight wire produces a magnetic field around it, and it doesn't really have a north or south pole, right? It's just circular magnetic fields around it. But if we see this coil as a plane, as like a disc, then it becomes an electromagnet, in which there is outward or inward field lines on like the right side of it versus the left side of it, if we see it as a disc. And so that electromagnet is going to have a north and a south pole, as opposed to a straight line or a straight wire where there's no north or south pole. But this one does have it, kind of like a solenoid. Think back to solenoids. So there is going to be forces between the coil and the magnet when there's this induced current in it. So the next question I ask is, what forces would the magnet and the coil feel during the magnets moving for A, B, C, or D? So I haven't labeled A, B, C, or D. I've only labeled A. So this is B, this is C, this is D. So we really have to see is like, where are there field lines exiting the right side of the plane, and where are they entering the left side of the plane, or vice versa? So in this situation, in A, I see my field lines are exiting like if we imagine the coil as a disc, they're exiting the inside of the coil on all sides, because I can even imagine if it were to happen all the way around, there'd be this, I think like this, right? Like that, because that's where the coil would happen. So it's exiting the right side of this coil. That means that would make this side kind of have a north pole and this side have a south pole. And that north pole is going to oppose, it's going to repel the north pole of the magnet. So we're going to see a repelling force for A. So this is repulsive. And let's just look where else we have that, right? When do we have that type of current? Well, it should be the opposite, right? We're adding a positive, that should be like removing a negative. So this will also create a north pole on this side and a south pole on this side. Again, just to like clarify, is we have magnetic field's going in on the left side and out on the right side, and it's happening all the way around. But except in D, that's a south pole right there. So that's actually going to create an attractive force, even though it has the north and south pole like that. So D is going to have an attractive force. Let's look at B. Well, we have magnetic fields going in on the right. That's a south pole over here. And then out, out on the left. So that must be a north pole. And that is producing an attractive force. So B is attractive. So we might imagine that the last one should be repulsive. And that's creating a south pole on the right and a north pole on the left, because we have inward magnetic fields on the right and outward on the left, It's pushing out on the left. And that's going to create a repulsive. Let's keep it in purple. And this ends this lecture. 21 minutes. So we started with how does the direction of the current produce, why is it in that direction? And it's due to conservation laws, This is really just a conservation of energy. This cannot happen because it breaks the conservation law. And our Lenz's law is shown by a negative in front of the Faraday's law equation. And then which direction, how to identify which direction depending on if you have an entering north pole, exiting north pole, entering south pole, exiting south pole. And this really could happen. It doesn't have to be a magnet and a coil. It could be any changes in magnetic field, any. So it could be two coils that have a current flowing through it as well. And then we decided the direction of the current and then which forces would occur according to this. I want you to also know that if you look at my OneNotes, there is another video that is quite extensive. It goes all the way to superconductors and shows very cool, almost sci-fi type science of how Lenz's law is applied to for magnetic levitation. So it allows things to levitate because any motion would produce too much current due to Faraday's law, and therefore produce an opposing force, and then so therefore things are held in place. And there's even a video, if you Google electromagnetism hoverboard, you'll find something. It's really silly, but you'll find something. All right, thanks for listening. We'll see you in class.